Hello again. We are going to be talking about calorimetry today, and basically we're going to be looking at the heat or the heat exchange when we're talking about different substances. So welcome back to another episode of this course in chemistry as we look at this activity, and we might be answering the question, what is the relationship between heat energy and temperature? You may remember from a previous video that I defined temperature. I mean, it's not my definition, but temperature is defined as the average kinetic energy of the particles of a substance. So Ke is kinetic energy. The line above it just means the average. So average kinetic energy of the particles. That would be a definition for temperature. So we're going to look at that and the heat energy. Heat is a type of energy that flows from from hot objects to cold objects. Okay? So when a substance is heated, the temperature increases. That should be obvious. Will the same amount of energy cause different substances to have identical temperature increases? Will the same amount of energy be needed to cause identical temperature increases in different amounts of the same substance? So we are going to be looking at mass, temperature, heat energy, and type of substance and see how all of them are related. In Model 1 we have a pot of water. This is before heating, and you'll notice that we're given a certain volume. We have 4 quarts. We have an 8 quarts pot here. We are measuring the temperature with this probe. Here we're measuring the temperature again. Then after heating for 5 minutes at a rate of 30 joules, that's a measurement for energy, 30 joules per minute, this is what we're going to determine down here. So we're going to heat it for 5 minutes. Let's answer some questions. In Model 1, which container holds more grams of water? Well, more grams of water would be the one that is the 8 quart in the 8 quart stock pot. Okay? So the larger one is going to hold more grams of water. Consider the process described in Model 1. How many joules of energy were added to the saucepan? We are adding 30 joules per minute for 5 minutes. So 30 joules per minute for 5 minutes. You can see that we have a total of 150 joules added in total. How many joules of energy were added to the stock pot? It would be the same amount. Both of them were heated for 5 minutes at 30 joules per minute for a total of 150 joules added. So it doesn't matter which one. Both of them were heated for the same amount of time at the same rate. Both of them are going to receive 150 joules. In which container did the liquid gain more energy, or did both gain the same amount of energy? Both of them are receiving the 150 joules over the course of the 5 minutes. So both of them gained exactly the same amount of energy. Okay? Both gained the same. For each container, include whether the temperature is expected to increase, decrease, or remain the same after heating. Well, we would expect, if you're adding heat, that we would expect the temperature to increase for both of them. Whether they increase exactly the same amount, that's yet to be determined. But when you add heat, if you heat these, we're going to expect to see this temperature here increase for both of them. Maybe not the same amount, we'll find out. So now we actually are going to see the data that was collected as a result of this heating experiment. So experiment 1, experiment 2, we have these different trials, A through F, mass here, 1 through 4, change in temperature, added joules of energy here. And down here, experiment 2, we got trials A through F. The mass is not changing, temperature change, added joules is changing. Okay? And here, experiment 3, trials A through F. Mass is changing, temperature is not, and added energy is changing. So you'll notice what we did here. Remember what we're trying to do. We're trying to compare mass, change in temperature, and energy for a substance, and they're keeping one of them constant and seeing the relationship between the other two. In the data tables in Model 2, what does delta T mean? That stands for change in temperature. Okay? Which experiment in Model 2 illustrates how the amount of energy needed to achieve the same temperature change depends on the mass of the water? Okay, so we're looking at which one of these, which experiment shows how the amount of energy needed depends on the mass of water to achieve the same temperature change. So we're looking for the one that has the same temperature change, and the amount of energy depends on the mass of water. So we don't want the temperature change to change. That would be experiment number 3. Here you'll notice that delta T is constant, so that would allow us to compare then mass and energy. Which experiment shows how different amounts of energy result in different temperature changes when the mass is constant? So which one has the mass constant? That would be here. That's experiment number 2. And then here's a key point for us. It says, why was it necessary to perform 3 experiments to find the relationship between mass, temperature change, and energy? Well, because we are, as mentioned, we are going to compare 2 at a time. So we're taking just 2 at a time, and we're pairing them up to see what the relationship is. If one goes up, what happens to the other one? And we're keeping the third variable constant. Question number 7 says, refer to experiment number 1 in Model 2 and consider the relationship between the mass of water, mass, and the observed temperature change when the same amount of energy is added. So we're going to go back up to experiment 1, and then we're going to look at these 2 questions. Let's just get a little preview here. Complete the statement below to show the relationship. We're trying to figure out when the same amount of energy is added to water at different masses, different water masses, the change in temperature, what's going to happen to that? Okay? And we're going to try to determine, is that a direct or inverse relationship? So again, we're looking at mass and temperature change when we have the same amount of energy. Experiment number 1. Energy is constant. As mass increases, the temperature change goes down if you keep adding the exact same amount of energy. 112 joules is always added to each of these mass samples here. Well, that means the change in temperature is going to be less when the mass is greater. Okay? Temperature gets smaller. That is an inverse relationship. As mass increases, change in temperature is going to decrease. Refer to experiment number 2 in the same model. Write a sentence that is going to describe the relationship between the observed temperature change and the energy required for identical masses, for samples that have the identical mass. So this time we're looking at experiment number 2, and we're going to kind of look at what kind of relationship we have here, looking back at our sample here in 7a. But this time we're looking at experiment number 2. Let's go up to experiment number 2, and we're trying to see our mass now is constant. Delta T, added energy. As this added energy increases, notice it's getting bigger and bigger as you go down here, what happens to delta T? Delta T is going to go up as well if you keep the mass constant. So added energy, delta T, that would mean that when you have an increase in the amount of energy, as energy increases, then the change in temperature is going to increase as well, and you can write that in a nice sentence like they did up here, and that is a direct relationship. In experiment number 2, should the value of the missing energy in the last row be larger or smaller than the other energy values in that column? So they left one blank here because they kind of want you to predict. Well, this should continue to go up, so it should be greater than 188 because the mass here, the delta T went up as well. And if we wanted to, we could actually graph these and make a better prediction as far as what this value of added energy would actually be close to. Okay? So the last row would be larger. And now we're going to look at experiment number 3. Write a grammatically correct sentence to describe the relationship between the mass of water and the energy, and this time temperature is not changing. So let's look back up at experiment number 3. We're trying to keep this delta T the same. So we have 1 gram of substance, and as soon as that temperature change gets to 9, we stop and we measure how much energy we added. We take a 2-gram sample. As soon as the temperature change is 9, we stop and we measure how much energy we added to that substance to get a delta T of 9. Well, as the mass increases here, you have to add more and more energy to get the same change in temperature. Okay? So, mass of water, as the mass increases, then the amount of energy that you have to add to that is going to increase as well in order to get a given set change in temperature. That would be direct as well. Anytime one goes up and the other goes up, or one goes down and the other goes down, that is a direct relationship. So we have here, in number 11, each of the experiments in Model 2 can be expressed as a proportionality, indicated by the following symbol. There's a symbol for a proportion. Several possible equations are shown in the table below. We're trying to see what is the relationship between each of these variables. We're taking 2 at a time, remember? Describe what each variable represents in the equation shown below. This would be your mass. This is your change in temperature. And Q is often used for our heat energy. For each experiment in Model 2, indicate which of the 6 proportionalities, we got 6 to choose from right here, shown in the table are correctly describe the relationship observed by the results in that experiment. Okay? So if we just remind ourselves that in experiment number 1, we looked at mass and delta T inverse relationship. Mass, delta T inverse relationship, that should be as one goes up, the other goes down. Mass and delta T, that would be this one right here. So that's showing an inverse relationship, that as one goes up, then the other's got to go down in order to keep this proportion, in order to make it work. Okay? In experiment number 2, we looked at energy and delta T. So Q and delta T, and this is a direct relationship. So we're looking for a direct relationship between Q and delta T. That would be this. And for experiment number 3, we looked at a mass and energy relationship that is direct as well. Mass and energy right here. Okay? So you might see where this is going. We are going to try to combine these maybe and come up with a formula. we've got 2 at a time here, but obviously there's going to be some overlap because we've got mass in experiment number 1 and we have it in experiment number 3. We've got heat in 2 and 3, and we've got temperature and temperature in 1 and 2. So now we might be able to combine them. We're going to write a single statement that includes all 3 variables. The statement should use Q as the variable on the left. So we're going to start with Q here. All right. Q is directly related, directly proportional to delta T, and it is directly proportional to M. And if you put T and M on the same side, then they're going to be inversely proportional. For example, if I was to multiply both sides by M here, right, I would get T and M on the same side. That tells me that that is an inverse relationship. So Q, I'm going to keep a proportion here, okay? Delta T and M. And I'm going to put a little operation there, that's multiplication. A proportionality statement can become an equation when a constant is determined. The equation will have Q on the left side, we got that, equal sign, and a constant C on the right side, we don't have that yet. So we're going to rewrite the proportionality statement from question 12, right up here, as an equation using C for the constant. After reaching a consensus, if you're in a group and you're using this in your group, we're going to look at the different possible answers here. So we've got our Q and our, I'm going to put the mass first and then the delta T, and right now they're just a proportion. If I want to equate them, then I have to multiply by some proportionality constant in order to make them equal, and I have now Q equals Cm delta T. These are all multiplied together, by the way. I don't need the little multiplication symbol, but it's there for you now. And now I have an equation. Again, Q is heat, M is mass, delta T is change in temperature, and this C is a constant for us that we're going to figure out what exactly does that tell us. Now we're going to take and we're going to solve for the value of C. In other words, we're going to rearrange this equation and get C all by itself. Okay? And then we're going to basically see what this constant really is representing. Okay? We'll plug in some actual data if we want to, and look at what that C value actually is representing. So I'm going to take this equation right here, and I'm going to divide by M and delta T in order to cancel it from the right, move it over to the left side, and solve for C. I divide this side by M and delta T. I divide the other side as well by M and delta T. This all cancels on this side, and I have C equals Q over M times delta T. I'm going to write it as C equals Q over M delta T. Okay, now let's look at the units here. You can plug in values if you want to from Model 2. You can plug in these numbers if you want to. You can plug in a mass, you can plug in a delta T, you can plug in the energy if you want to, and find out what the C value is. And you can do it for a whole bunch of these, and you're going to figure out that it is a value for that particular substance, whatever that substance is. That substance has a very unique C constant. So every substance has its own C constant, own C value. It is called the specific heat. And the units for that are going to be, Q is heat, that's joules. Mass, it's going to be grams. And delta T is degrees Celsius. So this is measuring here, this C value is measuring how many joules does it take to raise the temperature of 1 gram of substance by 1 degree Celsius. Okay? That's what this C value is measuring here, and it is called specific heat, and it is unique. Every substance has its own specific heat value. So the constant, as we just mentioned, is called the specific heat. It is an intensive physical property that has a different characteristic value for every substance. What that means, intensive, simply means it doesn't matter how much of the material you have. If you got a little bit or a lot of it, that value is going to be the same for however much of that substance you have. It is only dependent on the type of substance you have, not how much of it you have. What is the value for the specific heat of water? Well, let's take this data up here and let's plug in some of these numbers. Maybe you did this already. If you take any of these, let's keep a simple one here. 1, 9, and 37.6. So C is equal to 37.6 joules. 1 gram, and the change in temperature was 9. And if you take 37.6 and divide by 9, you're going to get the specific heat of water, because the substances that we're using in all of the experiments was water. So 37.6 divided by 1 divided by 9, and you're going to get the specific heat of water in joules per gram per degree Celsius. Okay? So using your equation for energy transfer, as we just found it out in question 13, and a calculated value for the specific heat of water, determine the amount of energy required to increase the temperature of 550 grams of water by 20 degrees Celsius. Okay, now that we've got our C value for water, you have to be told what substance you're dealing with so that you can use the specific heat value for that substance. Again, every substance has its own unique specific heat value. Q is equal to Cm delta T, and you have 4 variables here: Q, C, M, and delta T. You're going to be given any 3 of those, and you should be able to find the 4th one. So in this case, we are given mass, delta T, and we know the C value now. The C value for water is 4.18 joules per gram per degree Celsius. So that tells us we need 4.18 joules of energy to raise a gram of water by 1 degree Celsius. You've got 3 values right here. Plug them in and solve for Q. Okay, see how your C or Celsius is going to cancel, your grams are going to cancel, and when you multiply these 3 numbers together, you're going to have your answer in joules. Using your equation for the transferred energy and the specific heat, determine the values for the missing data in the 3 experiments in Model 2. Trial F in experiments 1 through 3. Okay, so there was a missing box up there, if you remember. There was missing data. But we can find that now using our equation. So we can find any one of these values given the other 3. And this is all for water, so our C value is always going to be 4.18 joules per gram per degree Celsius. So if you come back up here, here we have a missing delta T. I'm going to write our equation here. Q equals Cm delta T. This time I'm going to solve for delta T. So if I solve this equation for delta T is going to equal what? Q over C times mass. So you just have to plug in the energy. 112 goes in for Q. The C is 4.18 joules per gram per degree Celsius for water. So put in 4.18 for C, and the mass here is 4. And once you plug in those 3 numbers and calculate this, you will have the missing delta T for that box. Down here, we're finding energy, so this is just going to be our Q. You're going to have our times C, which is 4.18, times the mass, which is 3, times the delta T, which is 18, That calculation right there is going to give you that missing value. And down here, again, delta T. Our delta T is simply going to be the Q value, which is our energy, divided by the mass and the C value, 4.18 times 4. Okay, so that should give you the delta T that's missing there. Any three of these variables will be given to you, and you should be able to find the fourth using our new formula here for a heat exchange. Use your equation to calculate the following. So here's just a little practice. How much energy is transferred when 30 grams? You've got to recognize that as soon as you see the G, that's grams, so this is your mass, is cooled from 25 to 12.7. Now, you have two temperatures here. That means you have a beginning and an ending temperature. This would be your initial temperature. This would be your final temperature. And as a result, to find your delta T, you have to take your final temperature minus your initial temperature. Okay? So it is being cooled, actually. So in order to cool something down, you have to actually extract heat out of it. You need a mechanism that's going to pull that heat away. So far we've been talking about putting heat into a substance. Well, you can take heat out as well. You just have to have it have the ability for heat to transfer from something that's warmer to something that's colder. So we need a change in temperature here. We do that by taking the two values and subtracting them. 12.7 minus 25. That's going to be your delta T right there. So let's write this all out. If we have our energy, Q, is equal to 4.18 joules per gram per degree Celsius. That's the C value, the specific heat for water. We're told that this is water. That's why I'm using 4.18 times the mass, 30 grams, times the change in temperature, which is final temperature minus initial temperature. Always. Final minus initial. When you calculate this, and I'll let you do this on your calculator, this 12.7 minus 25 is going to be a negative value. So that's going to make this whole product negative. You're going to get negative something. What does that mean? When you get a negative value for your heat transfer, your heat exchange, that is simply saying that if you have your water, you got a container of water here, right? That heat is leaving that substance. If it's negative, if you get negative here, negative tells you that it is leaving the system. Heat is leaving the system, and that is telling you direction of heat flow. If it is a positive number, that means heat is going into the system, into the water or whatever substance it is. Okay? So that's a major significant difference between this value that we just calculated, it's negative, and the other ones that we saw. Alright, let's heat mercury this time and water. This time we're going to have two different substances. So we have to realize that water is going to have a C value, a specific heat value. Mercury is going to have its own separate specific heat value. They're not going to be the same. We just found that water's is 4.18. Well, we're going to have to find out if mercury, what mercury's is, or maybe it'll be given to us, but it's not going to be the same. We have 4 trials. The first 2 are with mercury, the second 2 are with water. Notice the mass is the same all the way through, and we're going to see delta T and added energy. Also, I'm just going to point out here, look at the added energy. Between trial 1 and 2, they doubled the amount of energy. Between 3 and 4, they doubled the amount of energy. That's not by mistake. That's a great designed experiment. You're keeping the mass constant, you're doubling the energy, and you're trying to figure out what happens to the delta T. Okay? What 2 substances are being heated in the experiments described in Model 3? Well, we've got mercury and water. compare any two trials in Model 3 that use the same amount of energy but involve different substances. Is the temperature change the same or different in the two trials? So we're going to take two at a time. We're going to compare same energy, different substances. So that would be trial 1, trial 3. Or you could use 2 and 4. Same energy. Let's take 1 and 3. Same energy, 1,000 joules for both of them. But here in 1 we're using mercury, in 3 we're using water. And it's asking, is the temperature change the same? Well, this one goes from, that temperature change is 71. Here the temperature change is only 2.39. No, not the same. They're totally different. Water's temperature went up only slightly compared to that of mercury's. Okay? Very different. Why? Because water has a different heat capacity, a different specific heat capacity than mercury does. Based on the data in this activity, the specific heat of water is determined to be 4.18 joules per gram per degree Celsius. Use data from Model 3 to solve for the value of the specific heat for mercury. Okay, we can do that because we have mass, delta T, and energy. So we can take any one of those, any trial that has mercury in it. We know that to find the specific heat, we need to take the heat divided by mass times delta T. So let's just take this one, 1,000 divided by mass of 100 and the product of 171. Okay? So if I was just to estimate, this is 10 over 70. So this is going to be about 1/7. Okay? 10 over 70, about 1/7. And our specific heat now, you'll notice that this specific heat is very, very small compared to the water's. This is a fractional amount of what the water's specific heat is. What does that tell us? This is telling us, remember what the units are telling us here. Specific heat is telling us how much energy does it take to raise 1 gram of the substance by 1 degree Celsius. So to raise a gram of mercury by 1 degree Celsius, it only takes 1/7 of a joule. 1/7 of a joule. Whereas for water, to raise 1 gram of water by 1 degree Celsius, it takes over 4 joules. Over 4 joules. That is an incredible comparison there. And water has a very unique ability to absorb a lot of heat without changing its temperature very much. If it has a high specific heat capacity, like water does, that's very high compared to mercury. What that tells you is water is able to absorb a lot of heat energy, and the temperature of those particles does not change dramatically. Okay? When adding the same amount of energy to two similar massed, not same substances, but the same similar mass, the substance with the larger specific heat will have a smaller temperature change. A large specific heat means it's able to absorb a lot of heat and the temperature doesn't change. If 23,000 joules of energy are used to heat water by 4 degrees Celsius, what is the mass of the water? Well, I'll set it up for you and you can do the calculation. If you're asking for the mass of the water, if we take our formula here and solve for mass, here, mass is going to equal Q over specific heat times delta T. So you're going to plug in the heat, 23,000 joules. By the way, just make sure that the units are correct units are being used here. This has to be in joules, not kilojoules. If it's in kilojoules, you have to convert it. And here you got specific heat, or sorry, you have, this is for water. So we have the specific heat of water, 4.18 joules per gram per Celsius. And the temperature change, you are by 4 degrees Celsius. Yep, we changed it by 4 degrees Celsius. That computation right there is going to give you the mass of that particular water sample. Okay? 23,000 joules of energy. Notice here we've got the same amount of energy, same temperature change. If I do this one, you're going to do basically the same thing. 23,000 joules over. Now this time you're going to have to use the heat capacity for mercury that you found up here, 1/7. About 1/7, okay? I estimated a little bit there. And 4 degrees Celsius. Now, I already can tell you that just knowing that the water has a higher heat capacity, that this energy right here to change the temperature of the water, this energy right here is compared to the same energy down here for mercury, and the delta T is the same. I know that this value here for the mass of the water is going to be a lot less than the value down here. I don't need as much water. 23,000 joules of energy are going to pour into a certain amount of water, and its temperature is going to change only 4 degrees Celsius, whereas you need 23,000 joules of energy to change this mercury. I know that this amount here is going to be much greater, okay? All right, let's look here. Here we have specific heat of aluminum. Okay, we have a different substance now, and we are told heat, we're told the mass of that aluminum, and we are told the temperature change. So again, we're just going to find our specific heat by solving our equation for C and plugging in. This is given to us in joules, good. This is given to us in grams and Celsius, excellent. So we got 4,750 joules over our 249 grams, and delta T is 21.1. Alright, you solve for this and you're going to get your heat capacity for aluminum, and it is going to be less than 1, just less than 1, which is not as small as mercury, but it's not nearly as large as water. Okay? So you can see here that water again has a very large heat capacity compared to mercury, which has a very small one, compared to aluminum, which has a heat capacity that's less than 1. Okay, it's greater than mercury, but much less than water. Okay, so let's think about the implications of that. Water is a great absorber of heat energy, and we use that to our advantage. For example, water is used in your vehicles in order to pull heat from your engine, so your engine doesn't overheat. So that water is circulated around the engine, and it pulls heat from that engine and then brings it to the front of your car, and it cools back down, the water that is, and then that water is recirculated and it absorbs heat. It pulls the heat away from your engine so that your engine stays cool. Okay? If you want to see how this works, you could take a balloon, blow it up, and hold it over a flame like a candle, and of course it's going to burst. But if you were to put some water in that balloon, it'll work. Blow it up, but have water in the balloon and hold it over the candle, it won't burst. Okay? So give it a try if you want. Water is a great absorber of heat. It has a high heat capacity, and this whole video is all about calorimetry, which is just the measure of heat as it deals with different types of substances. Alright, I hope you enjoyed this, learned a lot, and I'll see you in the next video.